Hi class, and we're back to lab next week with lab 5. Lab 5 deals with intermolecular forces and chemical reactions. Please note, as your lab schedule says, read the following sections of chapter 7 and chapter 8, and make sure, as always, you come with your lab notebook prepared and your lab worksheets filled out for your lab instructor to read or to review. Also, as always, of course, please read your experiment in entirety before coming to lab. You will also need to bring your textbook in order to understand solubility rules, so please bring that to lab as well. Alright, so let's get started with our pre-lab lecture. Some of this content may have not been covered yet in class, so please make sure you carefully go over this pre-lab lecture video as well as the sections designated on the front of your lab manual. Okay, so we have really two main goals for this week's experiment. The first goal is to test the properties of 5 solid compounds that you'll have in lab and determine which class of compounds they belong to. So what we mean here, class of compounds as in ionic compounds, metallic, molecular meaning covalent compounds, nonmetal compounds, or network covalent compounds. Another goal of this week's experiment is to really gain first-hand experience with different types of reactions. So again, you may have not gone over this in lecture yet, so please make sure to carefully read the sections and to review this pre-lab lecture video. So just as a review, we've gone over in lecture of 2 types of forces. We have intermolecular forces and intramolecular forces. If you remember, intermolecular forces are attractive forces that act between molecules, and the key word is between here. Intra are forces that act within a molecule. We refer to these really as bonds, not as forces, because they're really strong, and bonds are extremely hard, require more energy to break than simply an attractive force. Intermolecular forces are weaker than intramolecular forces, but they are actually strong enough to influence the physical behaviors, meaning they're strong enough to determine whether something's going to be a solid, liquid, or gas. Intramolecular forces, as we said, they're stronger than intermolecular forces. And finally, intermolecular forces are responsible for the states of matter, so whether or not a compound is going to be a solid, liquid, and gas, etc. As another review, the classes of compounds that we've discussed in lecture, we have ionic compounds, we have covalent compounds, oftentimes we refer to these as molecular compounds, and we have metals, and lastly we have network covalent compounds. Now, ionic compounds, as we said, are comprised of cations and anions. They're between metals and nonmetals, so it's really easy to actually detect ionic compounds simply by looking at chemical formula. See if there's a metal and a nonmetal, and if there is, automatically it becomes an ionic compound. Remember, with ionic compounds, we form ionic bonds through a transfer of an electron, or a transfer of electrons. It's not a sharing of electrons, it's purely transfer of electrons. And because ionic compounds are comprised of ionic bonds, they have usually very high melting points. And as just something on the side, which you'll be testing for actually, is most ionic compounds are good electrical conductors, and that's because ionic compounds result in electrolytes in solution, and electrolytes conduct electricity. In lab, you should have 4 models that you'll see in lab. One's an ionic compound lattice, and in that you'll see how you have spheres of sodium and spheres of chlorine atoms attracted to one another, and that's really what an ionic lattice looks like. We then have our covalent or molecular compounds, and we said that molecular compounds are comprised of, or are made up, of covalent bonds. One easy way to detect them is that molecular compounds or covalent compounds only occur between nonmetals. As we know by now, nonmetals share electrons. It's not a transfer of electrons, it's a sharing of electrons. And the way we recognize covalent compounds is that they're really comprised of discrete molecules. So as we said in lecture, if we take a look at this schematic here, we have discrete individual water molecules, and what brings these water molecules together are not bonds, it's hydrogen bonding intermolecular force, which is the strongest force that exists between these individual water molecules. Next up is network covalent compounds. So these are also comprised of covalent bonds because they share electrons, but instead of being discrete molecules, they're non-discrete in the sense that they're actually continuous structures. An example of that is diamond, and we showed this to you in lecture. Diamond is comprised of carbon atoms covalently bonded to one another. So it's actually a network of covalence, and that's why this class of compounds is referred to as network covalent compounds. They're extremely high in strength, which thus result in high melting points because it requires more energy, to break a covalent bond, whereas here all we really have to break or disrupt is a force. As we said in lecture, what you're held accountable for network covalent compounds in this class is quartz, which is SiO2. It's a network of SiO2, and an example of the SiO2 structure was given to you in lecture. You're also responsible for diamond, which will have an actual 3D model for you presented in lab, but here's a short schematic here. And also finally graphite, which will also have a schematic for you, so you can see the difference in how the bonds are arranged differently. They're both carbon, but they're obviously very different. Graphite's very flaky. Diamond is one of the hardest, strongest compounds we have, and it's really attributed to the way these different atoms are bonded in the lattice of a network covalent compound. One major characteristic of network covalent compounds is that it's insoluble in water. So ionic compounds are always soluble in water. Network covalent compounds are insoluble in water. The last class of compounds that we've talked about are metals. And metals are composed of lattice of positive ions. They're extremely high strength, and they're good conductors of electricity. And that's the reason is because really metals, you have these electrons are free to roam between one another. And as we mentioned in class, what allows for a metallic bond to happen is the electron cloud is now attracted to the positive nucleus. So now we're involving the nucleus of these atoms, and that results in a very, very strong, the strongest type of bond, which is a metallic bond. And that results in very high melting points, great conductivity. Another thing to note is metals are insoluble in water and organic solvents. Some exceptions are metals can actually dissolve in acids. So these are the 5 classes of compounds, just a review from what we've had already discussed in lecture. Again, please take a look at the 3D models that we're going to have for you in lab just to better visualize what the differences are specifically between ionic compounds, network covalent, and metallic compounds. All right, now let's go on to the individual parts of this experiment. So this experiment, we have 5 parts. Part 1, we have 2 parts for this experiment, 4 parts in part 1, 2 parts in part 2. So part 1 is the determination of intermolecular attractions. As always, please make sure to use tables to organize your observations. It's really important that your observations are very detailed so that they stand on their own, but also organized so that you can go back and review your notes. So in part A, we're really just looking at the physical observations of the 5 compounds that you're going to have. I want you to note the color, luster, if any, so if it's shiny, if it's dull, malleability, if any, or any other physical observations that you think may be useful. So be as detailed as always with describing your physical observations. In part B of part 1, we're going to look at the relative melting point. You're not actually measuring melting points. Here, we're going to give you kind of a scale on to assess how to actually figure out something's high melting point or low melting point. With part B, you're going to be using a hot plate. You're going to crank up the hot plate. You're going to make a boat out of aluminum foil, and here's a short picture of what this boat looks like. Have your lab instructor or TA help you with this. And you're going to put a little tiny spatula scoop of your compound in your boat. If it melts in less than 2 minutes, we're going to describe this as low melting point. So again, we're not looking for exact numbers, we're looking for low or high. If it doesn't melt within 2 minutes, we're going to attribute it to a high melting point. And as always, I want you to record your observations. So your initial observations, what it looks like before heating and what it looks like after heating. And I also want you from part B to correlate your observations, your melting point observations, to the type of compound that you have. An example, well, basically the type of compounds, is it a metallic compound? Is it ionic? Is it network covalent? Or is it molecular? Molecular, also known as covalent compounds. And correlate your melting point observations to the type of compound and see if it makes sense, if it's actually good correlation or poor correlation. And if it's poor correlation, discuss this with your lab instructor. In part C, we're going to assess the solubility. Is your substance soluble in water? Is it insoluble? Is it partially soluble? So again, you're going to be using a spatula tip amount. Remember, when we say spatula tip amounts, we're really saying something as small as the tip of this pen. So very, very small amounts. One thing that we've noticed, all of your lab instructors, some of you are not actually recording the amount measured. You're just saying, hey, 25 milliliters of H2O. That is incorrect, because your graduated cylinders are supposed to actually go, to 25.1 milliliters, for example, 24.9 milliliters, if you're sure you exactly measured 25, then it's 25.0. So make sure you measure and actually record the amount of water that you've used. We want you to record your observations and note if it's soluble or insoluble. So record observations. Don't just write same as before. That's incorrect. I want you to write down your observations. Did it dissolve? If it did dissolve, what does it look like? Did it not dissolve? Well, if it didn't dissolve, what does it look like? Remember, soluble means it's completely transparent. If it's semi-transparent, that means it's insoluble. You have very small, probably nano-sized particles floating around in your test tubes. Finally, for experiments for part 1, you're going to be conducting conductivity experiments of aqueous solutions. Now, if you remember in class on Fridays, during Friday's lecture, we said aqueous solutions are those solutions that are completely soluble in water. So you have a substance, it's fully dissolved in water, and it's predominantly made up of, again, water. Only perform conductivity tests on the soluble substances from part C, and any other substances, or any other solutions placed at station D. Please note, for a conductivity test, the light bulb is very faint, so you and your lab partner might have to kind of put your hands around the light bulb to really see if it's actually lighting up. Make sure you always wash the electrodes between runs, because if you don't, you're going to have residue and then you're going to contaminate the rest of the tests. So with the conductivity experiment, we're testing to see which aqueous solutions, again, I'm reminding you what aqueous solutions are. It's those substances that completely dissolved in water, contain electrolytes and non-electrolytes. Electrolytes, non-electrolytes, this might be new to you, so let's go over what they are. Electrolytes are basically any substance, or substances that that dissociate into ions when dissolved in water. As soon as you have ions in water, that conducts electricity. So an example of this in writing a chemical formula, we have sodium chloride, salt, so literally salt from your kitchen, sodium chloride. We're going to add it to liquid water. Remember, The substances are only in liquid phase if they're completely pure, and we know water is just water. This sodium chloride completely dissolves in water, and we know this because it's a completely clear, transparent solution. And when we have a clear and transparent solution, that means we have ions of this ionic compound, and we refer to that as aqueous. So this dissociates into sodium ions plus chlorine ions. When we write aqueous, that inherently tells us that we are in a solution of water, okay? So these ions conduct electricity. And since they conduct electricity, we call sodium chloride an electrolyte. A non-electrolyte are substances that may dissolve in water, but do not conduct electricity. And they do not conduct electricity because they do not dissociate into ions. So you can only conduct electricity if your substance dissociates into ions. So let's actually do an example here. An example is sucrose, otherwise known as table sugar. Table sugar has the following chemical formula: C12H22O11. So if we take a spoon or a spatula of table sugar, it's a solid, we add it to liquid water, it completely dissolves. Therefore, the way we would write this chemical formula is sucrose, but it's an aqueous, and again, this aqueous tells us that it's fully dissolved in water. We know sugar dissolves in water. This is something that everyone knows that's ever made a cup of tea or even coffee or anything of the sort. Now, if you were to put your electrodes into sugar water, you're going to see that the light bulb does not light up. And if your light bulb is not lit up, then it is a non-electrolyte. One important thing to note, and your lab manual says this: work with DI water only this week. And the reason is regular tap water has ions inherently floating around. DI water, DI stands for deionized water, meaning we've removed all majority ions from this water source. So therefore, when you're doing conductivity tests, you're really assessing whether or not a substance is truly conductive, if a substance is an electrolyte or not, a non-electrolyte. One thing to note, all ionic substances, as I said, are strong electrolytes, meaning your bulb should light up. All molecular compounds, except acids and bases, are non-electrolytes. So acids and bases are in fact electrolytes, and we'll cover that later on in the semester when we start discussing acids and bases. Sucrose is a molecular compound. It's a covalent compound. Therefore, it should theoretically be a non-electrolyte, and you're going to prove that in lab this week. So this is all the first goal of the experiment was to really understand the properties of 5 different compounds that you're working with. The second goal of the experiment is to really gain firsthand experience with different types of chemical reactions. We're reminding you again, always write initial observations of all your reagents used and final observations after a chemical reaction. Never write no reaction. You have to describe what you see, please. So let's review. How do we know a chemical reaction has actually taken place? Well, one thing, if you see a color change, a chemical reaction has taken place. If temperature changes, meaning did it get hot? Did it get cold? So feel your test tubes. Did a gas form? So formation of gas. This could occur either as bubbles or vapors on the side of your test tube walls. Another example of an indication of a chemical reaction is formation of a precipitate, which you've seen quite a bit a few labs ago. So formation in experiment 2, formation of a precipitate. Remember, a precipitate is an insoluble solid. Now, precipitates can be very obvious, which they'll just sink at the bottom of your test tube, or they might not be very obvious and they might just be floaties around in your test tubes. which brings us to a really important point. Make sure your test tubes are always clean before you use them, so that way your observations actually make sense. So in this week's lab, we're going to be working with two types of reactions. We'll discuss the other types of reactions in lecture. The first type of reaction, it's called a single replacement reaction. So if we were to look at the general nomenclature for this, we have a general chemical A reacting with another compound BX. Single replacement says one of these singly replaces with the others. So we swap A and B. So now we've created a new compound, AX plus B. So in part A of part 2, we're doing a single replacement reaction of zinc with hydrochloric acid. So another type of single replacement reaction, what if we have iron plus copper 2 sulfate? So part of your exercise after lab, which you are to pass in during GIL, is to actually write out your reactions in Word and then convert them to formula. So how do I know this is a single replacement reaction? Because I have a single component reacting with two components. Whenever you swap, you always swap the metals with the metals, nonmetals with the nonmetals. So here we have two metals, so we're going to swap these. So we end up with iron 2 sulfate plus copper. If you want to connect this back to your general formula, so this is my A, this is my BX, here I get AX plus B. You see that? Great. So let's actually convert this into a chemical formula. So this is my word formula. My chemical formula, we know iron, and it's a metal, so it's a solid. It reacts with copper sulfate. So review your notes, please, if you don't remember how to go from name to formula. Copper sulfate. When they swap, we get iron sulfate, and it's in aqueous form. I only know my phases when I actually make observations in labs. So the reason I know copper sulfate is aqueous, because it's a transparent solution. When I react it with iron metal, I get an also transparent solution, which I know it's iron sulfate. I also can use my solubility rules, which you can actually bring this with you to lab, which you actually have to bring with you to lab for the pre-lab lecture worksheet portion instead of bringing your textbook. So your solubility rules also helps you determine what's aqueous and what's not, and we'll go over this heavily in lecture. So let's just finish up our chemical reaction, and we'll see that there are solid bits and pieces in our test tube, which is copper metal. So again, in part A, you're doing a reaction of zinc with hydrochloric acid. All right, in part B, we're doing another type of chemical reaction called a double replacement reaction. So let's give the general formula. We have AX plus BY. This gives us AY plus BX. So again, note your cations here, which are your A and B. Cations replace cations. All right, so let's do an actual example. So my cations in this general formula were my A's and B's. And notice how your A's and B's swap here, or basically your X and Y's also can swap. So cations swap with cations, anions swap with anions. All right, let's do an example. So here we have potassium carbonate plus calcium bromide. Now, I need to determine what my products are. So these are my reactants. I know it's a double replacement reaction because I have 2 and 2, so they're going to swap with each other. So my cation will swap with my cation, so then I will get potassium, or my anion can swap with my anion. So I get potassium bromide plus calcium bromide. So let's pretend we're in lab for a second. This is a solution, it's completely transparent, and this is a solution, it's completely transparent. So when I go ahead and write my actual chemical reaction using chemical formulas, potassium, remember, is K plus, carbonate is CO3 2 minus. So therefore, when I write my chemical formula, my 2 swaps, my 1 swaps, so I get K2CO3. I see that it's a transparent solution, therefore it's aqueous phase, plus calcium bromide. Remember, calcium's 2 plus because it's in group 2. Bromine is group 1, so therefore it's -1. My superscripts swap, and I get calcium bromide. In lab, I see it as a transparent solution, so therefore it's aqueous phase. Now I write out my products here. Potassium bromide, so I have K plus and Br, and do these steps slowly so that your chemical formulas are correct. I get KBr, I'm not sure what phase it's in, plus calcium bromide, so again calcium's 2 plus. Oops, okay, this is actually supposed to say calcium carbonate. So calcium is 2 plus, carbonate is 2 minus, so I get CaCO3. So I don't know what my phases are because in lab, let's just pretend, in lab I mixed 2 test tubes that were both transparent, mixed them into one another, and now I have a solid in my test tube. So what's my solid? Is it KBr? Is it calcium carbonate? That's where your list of solubility rules comes into play. So your solubility rules are split into 2 tables, soluble in water, insoluble in water. Okay, so here we're saying that all sodium, potassium, and ammonium salts are soluble in water. All acetates and nitrates are soluble in water. Most halides are soluble in water except these halides of lead, of silver, of mercury. Most sulfates are soluble in water except sulfates of calcium, barium, lead, or strontium. Okay. Let's take a look at things that are insoluble in water, substances insoluble in water. Most phosphates, carbonates, and sulfides are insoluble in water except sodium phosphates, potassium, ammonium salts, or calcium sulfides. Most hydroxides are insoluble in water except sodium hydroxide, potassium hydroxide, calcium, and barium hydroxides. So given this table, we can now determine what the phases are of these. So our charts, our solubility rules chart says that most phosphates, carbonates, and sulfides are insoluble in water except if you have one of these. Now, calcium carbonate is not an exception, so therefore actually calcium carbonate is a solid. KBr, here we say all sodium, potassium, and ammonium salts are soluble in water. There are no exceptions, so KBr is aqueous.